Hey class, and welcome to part 2 of Building Envelopes and HVAC. This section will be covering components of the envelope as well as thermal resistance. So the last lecture we kind of finished off with the progression of R values of various constructions, uh, and you can see our tendency to love glass and steel hasn't done us any favors on the thermal envelope side of things. One of the important pieces that the envelope plays within the building energy system, I guess, is that if you think about a conventional building, and depending on your climate, where it's located, how you're using the building, and its overall site and design, you end up with certain thermal loads that you need to take care of, right? A certain amount of heating or cooling is required to keep people comfortable inside. And we use various systems. We'll get into that in the HVAC portion, but variable air volume, heat pumps, different means of providing heating or cooling, each of which take up, a certain amount of energy. And so this energy is going into systems, into the loads, and sure, we could spend a lot of money trying to optimize these systems, getting more expensive types of systems that use a little bit less energy, say replacing a VAV with a VRF system, something that's very expensive but also very efficient. That way we could, upgrade our systems and minimize our energy usage. But if we look at the building design a little more holistically, if we focus instead on downsizing our loads, we still have the same climate, maybe the same building use, but we design a little bit differently in such a way that we've reduced the amount of heating or cooling required in the space by having it be a tighter building, better insulated, then the systems not only get smaller and use less energy, we don't have to pay as much for them, right? Instead of asking for a big upgrade from one type of system to another, it doesn't matter the type of system because the overall loads have gone down so much, we can replace it with something that's going to use a whole lot less energy. The other piece that I think is important to consider about adding an envelope is the idea of a complex system needed to meet certain loads versus a very simple but resilient system. So say we have an unlimited budget, right? And we want to heat and cool a simple house, right? And on the left, we're just going to go all out from an engineering perspective. On the right, we're going to optimize the envelope. So say we want to get all of our hot water. We put in some radiant floors in the space based on just a solar thermal system, right? So evacuated tubes with hot water that's circulating through, just warmed up by the sun, very efficient. We don't have to pay for the sunlight. That's great. And say for the air side of the system, we added in a heat exchanger. So we're recycling a lot of heat while still getting fresh air in the building. And then just to top it all off, we add in a ground source heat pump, right? So we're recycling the heat from the ground. So during the wintertime, we're pulling kind of the warmish 60-degree, temperature from underneath the house, cycling that through our heat exchanger into heat pumps and warming up the space that way. During the summertime, that reverses. It's great. But it's also very complex. Whereas if we look at simply hyper-insulating our envelope, tightening up all the seals around everything, adding some attic insulation, insulating around the walls, maybe minimizing the amount of window exposure, we end up with a system that might use about the same amount of energy, even though it's using really old, boring, conventional systems to do that. But if you look inside, in our complex building, we might have a couple of different heat pumps, a heat exchanger, a whole lot of piping, whereas in our tight thermal envelope over here, we've got one much smaller, maybe a little less efficient, but much simpler system. So if the power goes out, it's going to take a long time for the heat to escape this building, whereas here, the heat might go out very, very quickly if we haven't optimized our envelope. And if there's a power outage, it's going to be a whole lot of work and an electrician and a plumber's nightmare trying to get all these systems back up and running, right? So I'd say that's one argument for really optimizing the thermal envelope. I'm all for these really cool, complex systems. I'm an engineer. I nerd out on this stuff, right? Ground source heat pumps are great. So are heat exchangers. But if you're just looking at it from a complexity versus a simple but resilient system, I think there's a strong case to be made for simply looking at the boring, unsexy, but very effective idea of hyper-insulating your walls, floors, and ceiling. All right, so how do we measure heat transfer in and out of buildings? I'm pretty sure the heat transfer course was required for you to be taking this, so you're probably very familiar with the R value, which is a thermal resistance to heat conductance at a steady state. And what we want for our buildings is a high R value. What do I mean by high? Well, let's just add in some kind of typical numbers here. Once again, I'm referring to the IECC 2015 code for commercial buildings. This is what's used in Idaho right now. For walls, we want them insulated at a thermal resistance of R20. Windows, they can get away with a whole lot less in R3. And this includes similar numbers for doors and skylights. For roofing, right now I think that's R38, but it's about an R40. And for floors, we're looking at about an R10. And these are in units of hours times foot squared times degrees Fahrenheit per BTU. It's a bit of an awkward way of looking at it, but it leads to some kind of nice round numbers that are easy for ourselves and builders to use. For floors, though, we usually break it into something a little bit different, the F factor, which I'll get into momentarily. The U factor is a measurement of thermal transmittance. It's essentially the same thing as the R value, it's just the inverse of it. But it's a very comprehensive way of looking at things. It is a coefficient of heat transmission, airside to airside, through a building component or assembly. So right now, in this office building, I'm looking at what is the air temperature outside versus the air temperature inside, and steady state, what is the BTUs per hour times foot squared degrees Fahrenheit that it takes to actually transmit heat through that wall or window. In terms of components, once again, U values are 0.05 to 0.09 for walls. Windows, this is actually how it's listed in code. So most oftentimes when you're looking for window transmission, you're looking at U of 0.38 to 0.45, roof 0.027, etc. Floors, as I mentioned, we use something called the F factor. It's kind of like the U factor, but instead of looking at hours times foot squared, we're looking at hours times feet, and it's the perimeter heat loss factor. This is used for slab on grade floors, and it oftentimes relates to the amount of insulation that's needed to be added around basically the slab perimeter of the building. So some kind of common numbers that you might see for U factors for walls: 0.064, windows 0.38, roof is 0.027. Our goal is to have as low of a U value as possible, right? The inverse of an R value. And you can see windows have almost an order of magnitude higher transmission coefficient, more so than the walls or the roof as required by code. So let's look at kind of a case study, if you will. If we're looking at kind of window to wall ratios, there's something called COG, or center of glazing, center of glass, where you are looking at the heat transmission at the center of the pane of glass. Whereas the overall U value of the window, which includes the assembly, is actually going to have worse of a thermal performance because oftentimes you're using metal framing, and heat transmits through metal quite often, quite quickly. So what if we replace some of the clear glass with a spandrel glass, something that has a slightly better insulation value? Overall, we're still just achieving an R5, whereas before we were looking at an overall R of 2.2. So we're not doing a whole lot better, but significantly better than just having it as all view glass, which is why you'll often see these spandrels in a lot of office buildings with curtain walls. If we replace even that clear spandrel with something that is a little bit more insulative, which has a center of surface R value of R15, then our overall R goes up to R of 9.8, so getting better, right? If we, you know, add even more spandrels around the windows, basically encase them a little bit more, uh, we're still just achieving an overall R of 9.8. And if we look at doing the very fancy, triple paned windows, which are very expensive, even this only gets us to an R value of 4 through the thermal envelope. So windows, they're great to look through. We spent a lot of time talking about the impact of daylighting in the previous section. I'm all for windows, all for looking out of them. They're great. I'm a huge fan of Mies van der Rohe and the very simplistic modern style of buildings with a lot of view glass in them. But just be aware that it has a pretty devastating impact on the thermal envelope. As engineers, maybe we would love super thick walls and no windows whatsoever, but that's not necessarily a pleasant place to spend a lot of time in. So there's just certain trade-offs that we have to be aware of. So spend some time looking at some of those typical R and U values, just so you have some kind of numbers that you can kind of scale against when you're doing recommendations or building audits. That'll give you kind of a general sense of what typical values are. Thanks, and look forward to seeing you guys next time.